Welcome back, ladies and gentlemen. Today we're going to be continuing with acceleration. You can find that, of course, in the general notes, but I've actually also, in your booklet, written up a fair amount on page 13. Um, Generally, this isn't always going to be the case, but for a lot of this early stuff, I managed to sort of type it up already. Later on, not so much. Anyway, acceleration. You guys would have worked with this before in grade 10, and it probably was the single most complicated thing that you did in grade 10. Acceleration tends to be a little bit confusing for most people for the simple fact that it's fairly abstract. It's hard to see, right? Like I can point at something and tell you, look, the markers are there. And you go, yes, I know. And then I can move them. And you go, hey, look, I moved the markers. And again, you go, I know. And I can move them slowly, like I just did, or I can move them fast, like that. And both of those you can see. You can see the slow, you can see the fast, you can tell the difference. But what people have a harder time doing is telling if the velocity is changing, if the object is getting faster and faster and faster and faster, or if it's slowing down more and more and more and more. And the reason for that is pretty simple. It's harder to observe and it takes longer, right? Like at a glance, you can tell where this is. I could, for example, cut the frame here, move the object and turn it back on, and you could tell that it moved, but you wouldn't be able to tell how fast I moved it. That requires you to watch it. So the combination of these factors tends to make acceleration kind of complicated. It's just hard to picture in your mind. So we're going to try and see if we can't explore that a little bit. The notes go into some pretty solid detail on this, so make sure you have a copy so you can take a look at them as we go. So, as it says here, acceleration is by far the most abstract of all of the grade 10 ideas. It is a measure of change in velocity with time. If we write it with math, it'll look something like this. A equals delta V over delta T. Now remember, delta V, delta T, the delta symbol, the triangle, means something. This whole formula can be rewritten as Vf minus Vi over Tf minus Ti. And these, of course, are vectors, and those are scalars. Now, this will be important for us later, but at the moment, the main effect of all of this is just that, well, okay, great, it's more complicated, I guess. There's more information there, or so it appears. But realistically, what does this tell us? The comparison between the final velocity and the initial velocity determines what the acceleration is. We're comparing two different velocities. So this allows us to break down this equation and find all the different ways that we can change it. And the key is change. It's change in velocity. So anything that changes the velocity is by definition an acceleration. Now, the units for this are usually done in two ways. Velocity is, of course, meters per second, and it's all over seconds. This is one way that you can write the units for this particular thing. Another way that we do it is that we sort of do a little bit of algebra, we merge these, and we get meters per second squared. Either of these is the same. They both mean the same thing, they both work. Each of them has their advantages. I mean, this one reminds you that the top of the equation is going to be velocity. This one is more compact, easier to write. So you can use either, they're all fine. So let's start breaking down our acceleration equation and see what we can piece together. Okay? The notes talk here about the fact that there are basically three broad ways that we can do this. Oh, I lied. Two broad ways that we can do this. The first way is that we change direction. Because remember, velocity depends on direction, right? There's a difference between me going this way at 10 and me going this way at 10. Both of them might be 10, but they're different directions. So we can change the acceleration, or I should say we would have an acceleration if the velocity has to change direction. You can sort of picture it as, say, the eraser here is moving along like so across the counter, and then it gets to a point and suddenly changes and starts coming this way. Well, in order for it to change from going, left and right here to going towards you guys, I have to apply an acceleration to adjust the velocity. So that's what it says here in the first option, a change of direction. The example that it gives, which is a really straightforward one, is that 10 meters per second north becoming 10 meters per second east is a change in the velocity. Even though the tens are the same, the norths and the easts are different. So that counts as an acceleration. Okay, so that one's the easy one. I mean, I should rephrase that. It is easy to explain, it is easy to forget, but broadly speaking, that's it. That is the first way in which you can have an acceleration, to change from going forward to going backward, or from going left to going up, or some other change. Now we're going to take a look at what happens, not when we change the direction, but when we change the velocity. Now, changing the velocity's magnitude is more difficult because we have a few options. I'm sure you guys know, you've seen in math class, right? If I ask you how can you change a number, most people will tell me, well, I can make it bigger, I can make it smaller, I can keep it the same. Now, keep it the same is by definition not a change. So keep it the same is off the table. So my two options are make it bigger, make it smaller. The only question is, how do we do that? So we're going to work through a series of examples, and we're going to piece together an idea. And when we get to the end of this idea, I'm hoping that you can see that there is something to it. Okay? All right. So first things first, we're going to do a series of calculations. And not going to lie, most of those calculations are on page 13. They're also located in the very notes that I am referring to here. But that's fine. I'm still going to do them because I want to showcase certain aspects here. Okay, here we go. We erase the board. Now, the first example talks about a kid on a skateboard. And the kid on the skateboard has got an initial velocity, and he has a final velocity, and there's a time involved. So if I check my notes here, so I want to make sure I'm using the same numbers as you guys. Says here, kid on a skateboard has an initial velocity of 1 meter per second. All right, so first things first, whenever we're doing any physics, we always want to draw a diagram. Now, the only downside here is you're about to discover that Mr. C can't draw, in case you haven't figured that out yet. But I'm going to try. So here we go. We're going to have a kid. There's our skateboard, and here's our child on the skateboard, right, obviously. And we'll give him a baseball hat. That's how we know he's a child, obviously. And it says here that said kid has an initial velocity of 1. All right, so we'll use another color here. We're going to have an initial velocity of plus 1 meters per second. Now remember, plus in this case would be right. So right this way. Then it says that we've got, it's going to take 3 seconds. Okay, so we'll do time here. We'll do it in orange. Over 3 seconds. Incidentally, you will notice, ladies and gentlemen, that I tend to use SEC for seconds to make sure that I don't confuse you and make you think that I just wrote 3-5, because my S's sometimes look a little bit like a 5. And then he has a final velocity at the end, I'll put that up high, a VF, little arrow, of plus 6 meters per second. Okay, we could, instead of writing plus, we could have written east, right, or north, or up, or forward. Although if you're using a skateboard to go up, you might have invented a hover skateboard, which is cool, but a little outside the scope of this question. So let's do some math, right? The math here should be pretty straightforward. We have our equation, A equals delta V over delta T. We then expand delta V because we have multiple velocities, VI and VF. So we need to expand delta V so we can actually fill it in. So we're going to get VF minus VI over delta t. Now I'm going to leave delta t small for a reason, which we're going to talk about in just a second. VF here is going to be plus 6 meters per second. Covering it up, I'm going to move out of frame here. Plus 6 meters per second minus plus 1 meter per second. Now notice this is, of course, the initial. This is the final. That means this part up here is good. Now, delta V should be initial minus final. What's the initial time in this question? You got to think about it for a second, because it doesn't actually tell us. It just tells us after 3 seconds. After 3 seconds is the final time. What's the initial time? 0. Very often when we're doing these kind of questions, we're going to make the initial time 0 for the very simple reason that it makes everything simpler, right? Like 3 minus 1, for example, wouldn't have been a hard math problem to do, but 3 minus 0 is a much easier math problem no matter what it is. So realistically, the delta t is going to be something like 3 minus 0. Okay? All right, so that means we're going to get 5 divided by 3. Now, if this was math class, you'd probably leave it as 5 divided by 3. I'm going to want to reduce that down. Let's make that equal to plus 1.66 meters per second squared. We tend to work in decimals in physics. We don't have to. We could go with a fraction, but for the most part, we tend to work with decimals. Okay, so we've done our first equation, and we clearly see something here, right? Now, this particular individual on the skateboard, they went from being slow, 1, to fast, 6. And we see that the acceleration is a positive number. So that seems like a pretty solid relationship, right? Like positive acceleration, you get faster. Let's work through a couple more examples, and we'll talk about that. So I'm going to write down up here, this is going to be equal to, we said, plus 1.66 meters per second squared. All right, now I want to do another one. We're going to deal with a dog. Okay, so we're going to have a dog, and that dog is going to be running towards the road, and then it's going to slow down. Okay, so the dog's going to run towards the road and it's going to slow down. I'm going to need a little bit of space here, not necessarily because I don't have room. I mean, I got lots of room over there, but I've got something in mind. I have a plan. So I'm going to erase this to make a little bit of space. Now, I have to draw a dog. I warn you, I can't draw. There's a reason I do not teach art. Okay, so here's our dog. Okay, obviously there's the back, there's the legs. That's how you know it's a dog. We're going to give it a squiggly tail, and there's the face of the dog, and it needs a nose. So there's our dog. It is the squiggle dog. It's a very illustrious breed, very famous. Now, it says here that our dog was running towards the road at 3 meters per second. Okay, so it was running. So that probably means that's the initial velocity. And then it comes to a stop. Okay, well, looks like I drew my dog backwards, though, because it's running in a forward direction. So that's okay. The squiggle dog is very adaptable. I can just erase his head and his tail, flip him around, give him some ears. There we go. And there's his tail again. Okay, squiggle dog is ready. We are going to go VI equals, it says here that I selected 3 meters per second. Then it tells me that in 6 seconds, so time equals 6, in 6 seconds, it comes to a stop. Now, by itself, that doesn't give us any numbers to put down. We have to know that comes to a stop means velocity final is 0. Comes to a stop or starts at rest, these are phrases that means that the velocity is 0 for a particular question. So make sure you keep tabs on that. Okay, we've got ourselves our numbers. Now we can start putting them in to the math. Once again, we've got a VI and a VF. Now we have to be careful here because, remember, A is equal to VF minus VI over T. I should put in some deltas. Don't be lazy, Mr. C. Okay, there we go. So which one is VI and which one is VF? We have to put it in the right place. Often at this point, a student will do something like this. 3 minus 0 over 6. Because why wouldn't you? That's super easy to do. It happens to be wrong, unfortunately. 3 is the initial velocity, not the final, and it goes final minus initial. So this won't work. Instead, what we have to do is we have to go a is equal to 0 minus 3 over 6. This looks weird, but this is how we have to set it up. And this is always the problem with the delta function, with the change in function, is that people miss pieces or they put them in the wrong order. This is one of the reasons why when I drew my diagram, I labeled the numbers so then I could take this and put it in the right place. It's always a danger if you're working on a piece of paper and you just have the numbers scribbled down, but you don't know what those numbers represent. Because then if you get lost or slightly confused, figuring things out after the fact is always incredibly difficult. So make sure that you are indicating clearly to yourself what's going on. That is why we draw pictures. That is why we list the information with the letters and the numbers. All of that is for a reason. Anyway, 3 over 6, that's pretty straightforward. That's going to be a half. Okay? So acceleration here is going to be 0.5. You could also, of course, leave it as 1/2. We're going to use decimals, though. Meters per second squared. But it is negative because 0 minus 3 is a negative number. So this is negative. Okay, so if we look at this particular problem, we can very clearly see that the boy on the skateboard has a positive acceleration and he is getting faster. And the dog has a negative acceleration and it is getting slower. So it seems like we have a very solid correlation, a very solid pattern that we can follow, which is always what we want to do when we're doing science. We want to find patterns. However, I am now going to show you what is called a discrepant event, something that doesn't fit the pattern we have so far. That doesn't mean that our pattern is necessarily wrong, but it might mean we need to expand it, that there might be something more complicated going on. So, for the last one, we're going to see if Mr. C can draw a bike. Now, we are going to have somebody on a bicycle, and the person on the bicycle is going to be right down here, and they're going to be I think I've got too many triangles today. Okay, we got a person, their legs, and then they're holding on here, and then they're here, and they're wearing a helmet, because of course you gotta wear a helmet. You guys are spending an awful lot of time making yourselves really smart. It would be a shame in which to hurt that head now. So there's our guy on a bicycle. Okay. Now, the question says that the guy on the bicycle has an initial velocity of 5 meters per second negative, which means he must be going west or something. Okay, so he's going this way. VI equals negative 5 meters per second. It also tells us his velocity final, and it tells us that his velocity final is this way. VF equals negative 10 meters per second. Finally, it tells us the time, and it says that the time is 5 seconds. Okay, there's our numbers. They're pretty much the same as the numbers we did previously over here, but they have negative signs. So how's that going to change things? Well, we'll very quickly scribble down some math over here. We know that A is equal to VF minus VI over delta T. A is going to be equal to, make sure we put the right ones in the right place. VF is first, so it's going to be 10, but it's negative 10, so we got to put a negative in front. This one is 5, so this is going to be negative 5. Now, this is often where people will stop, and they'll make a mistake here. Because, remember, the 10 and the 5 are negative by themselves, right? I could put them in brackets, like so. But what are we doing to these two numbers? We're subtracting them. That's peculiar. I mean, you guys have subtracted negative numbers before at this point. You know how to do them. It's 5 underneath here. But what happens? Well, negative and a negative becomes a positive. Negative 10 positive 5, well, that will be negative 5. So we're going to get negative 5 over 5. That's barely a 5. So that means that the acceleration here, we may as well write it right here, is negative 1 meters per second squared. Okay, well, the math was pretty simple on that, but now let's consider our theory. We said in our theory that most situations that we saw so far, and most situations that we saw in grade 10, had it where a positive acceleration meant that I was speeding up, and a negative acceleration meant that I was slowing down. But now I have a negative acceleration, and yet I go from 5 to 10. Now, I hope it doesn't take a physics teacher in grade 11 to tell you, but 10 is bigger than 5. They're both negative, so they're increasingly negative. They're getting bigger in the negative direction. That's weird. Based on our understanding with the dog here, a negative should be slower. He went from some number 3 to 0, but this guy's going from 5 to 10. Something fishy's going on. Now, as I said, there's a reason I did this in the exact arrangement that I did. Because there is still a pattern here. Unfortunately, my ability to draw evenly is not very good. But see previous comment about I can't draw. Right here, we have a positive velocity and a negative acceleration. And in this particular case, we are slowing down. Up here, we have a positive velocity and a positive acceleration. And up here, we are speeding up. Over here, we have a negative acceleration, and we have a negative velocity. And we are speeding up. There is one type of problem, one set of possible variables that I didn't do an example for. I didn't do a positive velocity with a negative acceleration. Whoops. I'm looking at that going, something's wrong here. I didn't do, let's try that again, a negative velocity with a positive acceleration. There we go. What will happen in that situation? Speeding up, slowing down, slowing down. There is the key. In grade 10, you basically only saw velocities that were going forward or in a positive direction, up, right, forward, north, stuff like that. As a result of this, you never really had to deal with accelerations that were negative. I should rephrase that. As a result of that, because you never dealt with velocities that were negative, you never had to deal with unexpected situations like this guy on a bike. Your situations were always very cut and dry because you were only ever really looking at half the problems. There's a whole other side of things. But we see in this situation that we have a pattern we can follow, and that pattern is key. If the signs are the same, these two, then you speed up. If the signs are opposites, these two, then you slow down. That's the key. If the acceleration is fighting the velocity, then it will slow the object down. If the acceleration is working with the velocity, it will speed the object up. So the guy on the bike is getting faster because he is pushing himself forward, and his acceleration is going forward as well. In this case, forward is west. Meanwhile, the guy on the skateboard is going forward because he is pushing forward, and his velocity is pushing forward. It just happens to be east. The dog is slowing down because the velocity is forward, but the acceleration is backwards. They're going in opposite directions to each other, so they fight each other. The yet unnamed example up here is the same. The object was going forward, but the acceleration was going, if I can get my hand in the right way, backwards. Opposites slow down, same speed up. Doesn't matter if it's same this way or same this way. If it's velocity one way, acceleration the other, or velocity one way, acceleration the other. I can flip it around. Doesn't matter. If they're the same, you speed up. If they're different, you slow down. And that's the key. That is the piece that is going to take some practice, some getting used to. So if we summarize all of these points, if the direction changes at all, even a tiny bit, you have an acceleration. You have to. If the object gets faster or slower, you have an acceleration. You have to. The only question is, which direction is the acceleration? And that you will have to figure out. Okay, that's it for acceleration. Right now, if you guys take a look, as mentioned, page 13 kind of goes over all of this. The same example with the person on the skateboard and the dog are all right there. Also on the back of page 13, on page 14, you see that there's a little chart for you to map out this very thing that I put on the board. But you don't have to put it here. You can put it in your own notes or just read it off of my notes. After that, on page 15, you've got some examples that you can try to do dealing with acceleration. The examples continue on page 16 with answers at the bottom and page 17 with answers at the bottom. And then you will notice that the next page, page 18, is kind of the start of the next part of the unit. Now, normally I would put a test at this point. I'm not going to do that this year. Instead, I think what I'm going to do is that the check your understandings have been made mandatory, and there is a single check for every single one of the pages and lessons that I've now done. So you guys can do those checks and get the marks for that. Next video, we're going to talk about graphing. And the graphing unit is going to take us a bit. We're going to have a lot we have to do in there. Graphing, of course, is going to be graphing of all the things we've already talked about: displacement, velocity, and acceleration. You probably didn't do that last year. We're going to be exploring graphs and how to use them. Once we finish graphing, we are done the introduction of physics. So I will leave it to you guys there. See about getting some work done. You should be able to do everything up to page 18 as soon as you finish watching this video. See you guys next time.